Hello everybody, my name is Satoshi Hoshino. I am from Utsunomiya University, Japan. The title of my presentation is Brain Mobility Interface based on deep learning techniques for classifying EEG signals into control commands. Okay, so we have thus far developed different types of CT transporters, as you can see here in this picture, which are called personal mobility robots, PMRs. These robots are equipped with a 3D LiDAR sensor here, and RGB camera here, and joystick. So as you can see here in this movie, the personal mobility robot PMR is autonomously moving toward a destination through some given waypoints. On the other hand, the user can manually control the PMR through the joystick. However, it is difficult for users with their hands full to grasp the joystick. In this case, we believe that mental commands are more useful to control the PMR. Therefore, we focus on EEG signals in the brain. From the EEG-based brain signals, the user's intentions are estimated and interpreted as control commands. This is a so-called brain-machine interface, BMI. Okay, in the proposed brain mobility interface, which is also abbreviated as BMI, a user wears a non-invasive and head-mounted EEG device. Measured EEG signals from the user are fed as inputs to control command classifiers. The classified commands are then sent to the PMR. As can be seen in this picture, the EEG device consists of electrodes, for example, here and here. At each electrode, a brain potential over time is measured as the EEG signal. The brain wave frequency of the measured EEG signal varies in accordance with the concentrated and relaxed states. So we focus on the following two types of EEG signals: when the user concentrates and relaxes and faces to the right, left, and front. For the input EEG signals, the brain state and face direction are estimated by the classifiers. Since the brain state and face direction indicate the user's intentions to move or stop the PMR in any of the right, left, and forward directions, the user's intention is simultaneously estimated. For example, move or stop in the direction. Depending on the estimated intentions, the EEG signals are finally classified into the control commands as the output. For this purpose, two control command classifiers based on deep neural networks, DNNs, are applied to the BMI. Each of the control commands is composed of linear velocity v and angular velocity omega. In order to correctly classify weak and noisy EEG signals into control commands, we use the following two deep neural networks. The first one is feed-forward deep neural network, which is FDNN, used as a linear velocity command classifier. And the second one is convolutional neural network, CNN, which is used as an angular velocity command classifier. In the convolutional layer, signal features are extracted from the EEG. On the other hand, such signal features are not extracted in the FDNN. So as an alternative to the convolutional layer, first Fourier transform, FFT, is performed on the measured EEG signals, and the frequency spectra of the EEG signals are used as the inputs. Okay, so as for the linear velocity command classifier based on FDNN, feed-forward deep neural network, the user concentrates on moving the PMR or relaxes to stop. Because the EEG signals in the concentrated and relaxed brain states are formed by high beta to gamma bands and alpha to beta bands respectively, the frequency spectra from 1 to about 50 are extracted as the signal features of the EEG and used as inputs, as can be seen in the following figure. The EEG signal measured at each electrode is transformed to the frequency spectra S through the FFT, where N represent the number of electrodes and F minimum and F max represent the lower frequency and upper frequency. Each of the nodes in the input and hidden layers is fully connected to the ones in the next layer through a weight. In these layers, the LEL activation function is applied to all the nodes. The output layer consists of two nodes corresponding to the concentrated and relaxed brain states. In the output layer, the softmax activation function is applied to each node in order to compute the probabilities of P1 and P2. Thus, the user's intention, move or stop, is estimated from the brain state with the higher probability. Depending on the estimated intention, the discretized linear velocity command V1 or V2 is determined as the output. Okay, so as for the angular velocity command classifier based on convolutional neural network CNN, the user faces to the right, left, or front to move the personal mobility robot PMR in the right, left, or forward direction. So the time series EEG signals when the user faces in the three directions are measured at all the nodes. In this figure, the EEG signals are measured by in total 1 to n electrodes. As an example, the time series EEG signal in t seconds at the first electrode is stored into the first row in the input format. Given the sampling rate and measured EEG signals, each row consists of FT elements in total. And for n electrodes, the input format is a two-dimensional array. Here, B and T represent the potential measured at the T sampling step by the nth electrode. The two-dimensional time series EEG signals are then fed as inputs to the angular velocity command classifier. First off, the input format of n times ft is represented by the h times w times one channel data. From the input 2D time series EEG signals, the signal features of the EEG, depending on the phase directions, are extracted through the convolutional and pooling layers. The extracted signal features are inputted into the fully connected layer FC1 and FC2. In these layers, the LEL activation function is applied to all the nodes. The output layer consists of three nodes corresponding to the right, left, and front face directions. In the output layer, the softmax activation function is applied to each node in order to compute the probabilities of P3, P4, and P5. Thus, the user's intention, move the PMR in the right, left, or forward direction is estimated from the face direction with the highest probability. And depending on the estimated intention, the discretized angular velocity command omega 3, 4, or 5 is determined as the output. Okay, for network training of the FDNN and the CNN, training data sets are collected from a user as shown in this picture. The user is now lighting on the PMR and wears a head-mounted EEG device, Emotive Epoch Plus, with 14 channels. So in total, 14 EEG signals are measured for 2 seconds. The sampling rate is 256. In total, 2,000 and 3,000 datasets were collected for supervised learning. For the linear velocity command classifier, EEG signals when the user concentrates and relaxes are measured. And as shown in these figures, the EEG signal measured at each electrode is then transformed to the frequency spectra through the FFT. And for these inputs, the brain states concentrated or relaxed are annotated. For angular velocity command classifier, EEG signal when the user faces to the right, left, and front are measured as shown in these figures. And the time series EEG signals are then annotated as right, left, or front direction. The network training proceeds so that both the FDNN and the CNN estimate the annotated brain state and face direction. If the network training proceeds correctly, the FDNN and CNN are able to gradually estimate the brain state and face direction of the user for the input EEG signals. These figures show the loss of the FDNN and the CNN based on the cross entropy. And these figures show the accuracy of the FDNN and the CNN. As the training epoch increased, the loss decreased and the accuracy increased. These results indicate that the connection weights and the convolutional filters in the FDNN and the CNN were successfully optimized. As a result, the estimation performance of both the FDNN and the CNN was more than 99%. So the FDNN and the CNN that minimize the loss are used as the linear and angular velocity command classifiers. This picture shows the target environment in these control experiments. The user wears the EEG just around here device is riding on the front wheel drive PMR. In this environment, the user mentally controls the PMR so as to move in the clockwise and the counterclockwise directions along the course. Depending on the estimated brain state and the user's intention, the linear velocity command to move or stop and the angular velocity command to move the PMR in any of the 3 directions are determined, as you can see here. Okay, here let me show you a movie that the user is controlling the PMR in the clockwise direction. At the initial position, the user faced to the front and concentrated on moving the PMR in the forward direction. Around each corner, the user faced to the right in the clockwise direction. And finally, the user relaxed to stop when the PMR arrived at the initial position. In this experiment, the classification performance of the BMI was 100% in the clockwise direction and 99% in the counterclockwise direction, respectively. So the results showed that the PMI performance was enough for the user to control the PMR as intended with only the mental commands. Okay, that's it. Thank you for your kind attention.